All right, so in a previous unit, when we talked about a particular function and be able to take its derivative, we called it differentiable. And we knew that a function was differentiable as long as there were no sharp turns, as long as there was no vertical tangent lines or no discontinuities, right? Okay, um, integrable, as far as functions being able to take the integral, I want the limit of my Riemann sum to exist. I'm going to know that my limit of my Riemann sum is going to exist if it meets this criteria. If a function f is continuous on a closed interval, so I'll stop right there. As long as you have a continuous function, you know you can take the limit of a Riemann sum. You can take the definite integral of it. It's integrable. Or if f has a finite number of jump discontinuities, then f is integrable on the closed interval from a to b, and the definite integral from f of x dx exists. What? Okay, let's look at that last part here. You have a finite number of jump discontinuities. I've got a picture of that right here, some sort of step function. The reason why you can still take the definite integral is because we're finding the area underneath a curve. And just take a look here. This one in particular is just a series of rectangles. You can imagine that your function is a lot more complicated than that, but you can just break it up into little pieces that you can find the area of. So let's write one for this particular example on the screen. So I would have the definite integral from, this is going from -5 here to 5, 6, 7, 8 to 8. So from -5 to 8 of your function, whatever the heck it is, with respect to x, should be equal to, and then it's a bunch of rectangles. Anything that's up above, I'm going to sign it as positive. Anything in red down below, it's going to be a negative. So up above this very first one, from -5 to -2 here, this has a base of 3 and a height of 3, so this one is a 9, an area of 9. Okay, on the next one here, it has a base length of 1, 2, 3, 4, 5 here, and a height of, looks like 2. A 5 by 2, that's going to give me 10, but since it's down below, I'm going to sign it negative, -10. All right, and then I'll break this up into two smaller pieces. It looks like a square because it's a 2 by 2, +4, and then I have 1, 2, 3, a 3 by 5, so that one is a +15. Why don't you put a plus sign here? Okay, so subtracting here, that gives me a -1. That is 19 for a total of 18, right? So there you go, integrable functions. So what I did on this particular example is understanding or making a connection between the definition of a definite integral, limit of a Riemann sum, and the fact that you're finding area underneath the curve. So here, these are just simple rectangles, so we could just use geometry to find the area. Okay. Another thing that we want to make sure that we're able to do is go back and forth between the limit of a Riemann sum, like this thing, the limit of a Riemann sum, and the notation for the definite integral. I want to be able to go bounce back and forth between those. Chances are that will be like a multiple choice type of question on your AP exam. So let's look at a few examples of this. Right here. Oh, yeah, hey, I forgot about Leibniz here with his definite integral. Okay, so a couple of things to remember about this. That definite integral, when we evaluate it, we're going to get a number. And what does that number represent? If your function is completely above the x-axis, it's specifically the area underneath that curve up above the x-axis, but some of it may be down below, and so here we're going to call it the net area that's bounded by your function f of x and, the x-axis. Why is it this stretched out looking S? Well, Leibniz here chose that thing because it is a limit of sums, right? It's the sum of all of those things, and you can see that this thing looks like a stretched out looking S. It looks a heck of a lot better than this guy. Anyway, all right. Rewrite each limit as a definite integral. We do not have to evaluate it, we are just rewriting it. I think the easiest part of this is to recognize this part that's on the outside here. We've got a limit, we've got our summation here, so this must be our Riemann sum, where we've got f of stuff, and then this thing is supposed to be our delta x. That's our width, right? So for this very first one here, our delta x is equal to 3 over n. And that's significant because we're going to use that in order to figure out what our b minus a over n is. We need our b and our a because those are supposed to adorn the lower and upper limits of our integration, those two things, okay? And the distance between those things has to be 3. So the difference between these has to be 3. We just have to figure out where is it supposed to start because there's no indication in here where it starts, or is there? It is all in the fact that we are taking multiples of our width. Starting from where? Well, look at the one that's right down below here. Here's our width, just like before, but this one is not simply just multiples of the width. It's starting with some 1 value here. Okay, and the reason why that is because, in general, your x sub I, or as we defined it in a previous slide here, c sub I, that's the number that you're going to plug into your function in order to find the height of your rectangle, which could be the left, the right, the midpoint, or any point on your subinterval. That's equal to, if your partition is regular, your starting value, a, and then you're going to start adding in multiples of the width. So that's I times your delta x. Okay, so in all the other examples, we started with 0. We started at 0, and so all we had were the multiples of the widths. So if we take a look at this example right here, right? Again, we started at 0, so we were just taking multiples of the width. On example number 1, same exact thing happened as we started at 0, and then we were just adding in multiples of the width. What if instead we started someplace else? If we started someplace else, then we're going to get one like question number 2. And so we'll address that in just a minute. So here we can see that our a value is 0. And then to get our b value, all we have to do is add 3 to that 0. So it's going from 0 to 3. Okay, and then you can kind of just squint down and you can see the function here. We are plugging this 3 over n into our function, and our function is an x squared minus 2 times x. And then don't forget to close it off with your differential, your dx. Okay, so the next one here, we're going to see what happens when we don't start at 0. So if we have some sort of graph, and I'm just going to make something up here. And let's say that I start that graph at 1 instead of at 0 whenever I go to draw my rectangles. And you know what? The function does not have to start at the x-axis. Maybe it looks sort of like that. What happened to it? Maybe it looks like that. Okay. And then I'm going to start drawing some sort of rectangles in here, using the right endpoint, as we do. Right, and then, you know, shade them so they look nice. Okay. So then, if I wanted to find the heights of each of those rectangles, and I'm going to plug in this point here, it is 1 width, right? So it's 1 width. In this case, the width here, just like the width of the previous one, is 3 over n. But I don't plug in f of 3 over n into the function because what I would get is that height way the heck over here, right? Actually, 1 right over here because it's to the right of 0. But this one starts at 1, so we need to add that in first. It's 1 plus the width. So inside the function here, erase, 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 this should be 1 plus our width. And then you'd have 1 plus 2 of the widths, and then you'd have 1 plus 3 of the widths, right? You're always starting from this a value and then adding in multiples of the widths. It's just that all of the other ones that we've seen so far, we started at 0. Okay, so this gives us our a value here. Our a value is going to start at 1, and just like before, the width, this b minus a, is going to be the 3 because these two widths are exactly the same. So we're going to be 3 more up from this one. What's our definite interval integral going to look like this time? Definite integral from 1, add 3 to that, 4, and now our function is exactly the same as what it was before. Here is your c sub I. This is your right endpoints stuck in here for x. This is your x squared minus 2 times x. And then cap it off with your dx. All right, we got a couple more of these things. I think I go in the, do I go in the opposite direction yet? No, of course not. All right, some of these are going to be even easier to pick out of a lineup as to what the definite integral is going to look like. So once again, you can see that they factored out the 2 over n. This thing must be our delta x. That's there. This is our delta x. They pulled it out in front of the summation because that's usually what we do as well, right? And then here's our function. And we can see that inside of the function, it's just multiples of the width. So where must they have started this definite integral? If it's just multiples of the width, then there's no like 1 plus or 2 plus in front of it. It's got to start at 0. So this is the definite integral from 0 to 2. Why is it from 0 to 2? Because the width here is only 2. The b minus the a over n is only equal to 2 over n. So if my a here is 0, then my b must be equal to 2. All right, and then my function is just e to the, and here is the width that are the x value that I'm sticking in there. In this case, the right endpoints. That just looks like e to the x. As it sits right now, the other ones we could have found by working out by hand, but this e to the x, not so much. No, so there's got to be another way to evaluate it, hopefully. Okay, next one here. Man, we got another width of 2 over n. So we know that our width is going to be a width of 2 of our whole entire interval here. But where does this one start? This one is going to start at 1. Here's my a value. And we're adding n multiples of the width to that 1 into the function natural log. So this one, we'll have the definite integral from 1, our starting point, add 2 more to that. That one's going to go to 1 to 3. And our function is simply the natural log of x. Right? Here's multiples of the width plugged into our function, and then cap it off with a dx. There you go. And like I said, it would be highly, highly likely that you would have to do something like that on the multiple choice section of the AP exam.